Hello and welcome to the final topic in Math 19661. This final topic is probability. So in this first video on probability, I'm going to introduce the mathematical theory of probability, including some of the basic concepts such as the sample space and events. Probability is a very important topic because whenever we're dealing with any sort of real-world process, there's always some amount of uncertainty. And we want to be able to understand this uncertainty. Of course, something's uncertain, we can't predict what is going to happen, but we want to be able to quantify how much error we would get in given experiments, how many times we might have to do an experiment over in order to be certain of the results, if we have a certain amount of error, and so on. And so this is areas within probability and to some extent within statistics. And so we're going to go over some of the basic ideas, basic definitions of probability. In this class, we're not going to get very deep into it, but this is laying the foundation for mathematical theory of probability. So the first concept is called the sample space. If we do a given experiment, or think of making some measurement, then the set of all possible outcomes of that experiment is the sample space. So within the sample space, we make a measurement, we get a particular value, or we make a particular observation of something that happens, and that's an event. And mathematically, in the theory of probability, an event is a subset of the sample space. So the sample space is the set of all the possible outcomes, and then an event is a subset. When we think of making an observation, we know then one of the possibilities in that subset has occurred. Roughly speaking, that's the intuition here. So as an example of this, suppose the experiment is that we toss a coin 3 times. So the sample space for this experiment would be the list that's shown here. We either have 3 heads, heads, tails, heads, or any of the other possible outcomes of flipping a coin 3 times. There's 8 different possibilities. That's 2 to the third because each flip has 2 possible outcomes. All right, and so that would be the sample space for this experiment, flipping a coin 3 times. An event, one possible event, might be the event that we observe there is exactly 1 tail out of the 3 flips. So we do the experiment and we get exactly 1 tail. And so this event would be the subset of all the possible outcomes of the experiment, the subset of the sample space in which there is exactly 1 tail. So there's 3 possibilities here. Tails on the first flip, tails on the second flip, or tails on the third flip. Another example of an event, which I'm going to label E2 here, is that we get a tail on the third toss of the coin. And so there's 4 different possibilities where we get a tail on the third toss, heads, tails, heads, tails, 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 heads, tails, or tails, tails, tails. And the only thing that's important here with E2, this event, is that all of these have a tails on the third toss. And these are 2 examples of events in this experiment with this sample space. Okay, we say that an event occurs if the outcome of the experiment belongs to that corresponding subset. So as I was explaining before, this is the intuition of the event. Events can often be written in terms of other events, and this is where we start seeing the mathematics of the situation. We start combining events together and see what happens when we do this. So for example, using the experiment and events described on the previous slide, the experiment being tossing a coin 3 times, E1 being the event where there's exactly 1 tail, and E2 being the event where there's a tail on the third toss. Then we can combine these to the event where both of those events occur, E1 and E2. That's, we have exactly 1 tail and it occurs on the third toss. So this is 2 heads followed by a tail. We say E1 and E2. And we use this notation, this mathematical notation, with the upside down U. In terms of set theory, that's the intersection of 2 sets, the elements that are common to both of the sets, the outcomes that are common to both of those events, E1 and E2. Right? Another way to combine 2 events is taking their union. And in probability, we call this the OR operation. So we say either E1 has occurred or E2 has occurred. And these are all the possible outcomes that are in one of the 2 events. This is the union of the two sets, thinking of the events as sets. And so this event we would say as E1 or E2, meaning that at least one of E1 or E2 occurs. Okay, and so remember the intersection operator here with the upside down U means and in probability. E1 and E2 occur. The union, taking the union of the two sets, the two events, means or. Either E1 occurs or E2 occurs. Okay. So here's another example. Suppose the sample, or the experiment rather, this time is rolling a dice twice, or rolling two dice, let's say. The sample space is then the set of all possible rolls you would get on the two dice. And they're ordered rolls, so the first one of these, it represents the roll on the first die, and the second, the roll on the second die. And this first outcome will be roll 1 on the first die, and then 1 on the second, 1 on the first, then 2 on the second. And altogether, there would be 36 possibilities. So you roll 6 possibilities on the first die, and 6 possibilities on the second. That's 36 total. All right, so that would be the sample space for an experiment rolling a dice twice, or rolling 2 dice. And let's suppose we consider an event, which I'll label here as A, which is a total of 7 is obtained. So if you roll the numbers, you add the numbers for each of the rolls together, you get exactly 7. Then this event, A, is this set of outcomes, the set of these pairs where they add up to 7. So 1 plus 6, 7, 2 plus 5 is 7. And these are all the possibilities out of the sample space where the two rolls add up to 7. Another possible event would be here, B. So this is just a list of outcomes that are in the sample space. It's a subset of the sample space. And so you can think about what would the description of this event be in words. I'll give you 1 second to think about it. You can pause the video if you want. All right, well, this event would be at least 1 3 is rolled. The thing that's common here is that these are all the outcomes, all the pairs of numbers between 1 and 6 where there's at least 1 3. So a 3 comes up on one of the dice. Okay, so let's talk a little bit more about operations with sets and subsets. So you can think of these in probability as operations with events. So the first concept we'll discuss here is the complement of an event. So we have a sample space, and an event is a subset of the sample space. The complement of that event is the set of all the outcomes that are not in the event. And so we take a given event and take all the outcomes that aren't in the event. So for example, remember E1 was the event that exactly 1 tail was flipped out of 3 coin flips. The complement of E1 would be either no tails are flipped, 2 tails are flipped, or 3 tails are flipped. Those are all the cases what could happen if it's not exactly 1. Another example, the other event we looked at with the experiment of flipping a coin 3 times was a tailed on the third toss was E2. The complement of that event would be a head on the third toss. So all the outcomes that are not in E2 would be the ones that have a head on the third toss. All right, and so we've already discussed the union. So in probability, union is or. So if either A occurs or B occurs, that corresponds to taking all the outcomes which are in one of the two sets, either A or B. And in probability, we refer to this as or. Sometimes when we're just talking about set theory, we would say the union of the two sets. Right, and then the other operation already discussed is the intersection. So you have two events, A and B. The intersection is denoted with the upside down U, and in probability we say A and B. It's the event that both A and B occurs. All right. A special event is the so-called empty set. We do consider this to be an event. Is that there's no outcomes, a set that contains no outcomes. We call this the empty set or the null event in probability. All right, another bit of terminology in probability is that if the event A and B, that's A intersect B, is equal to the empty set, or the null event, then A and B are said to be disjoint or mutually exclusive. That means that if A occurs, then B can't possibly occur. There are no events or no outcomes that are in both of the events A and B. All right, so since the outcome heads, heads, tails is in both the events E1 and E2, remember that was E1 and E2, the example we discussed, that means that these two events, E1 and E2, are not mutually exclusive. And so it's possible that both E1 and E2 could occur. Right, on the other hand, if you have an event A, then the complement of A is always mutually exclusive from A, whereas A and A prime, A complement with this prime notation or dash notation are always mutually exclusive. You can't both have an event occur and its complement occur. It's just from the definition of the complement, it's all the outcomes which are not in A. Okay, so look at an example now. Another example. Suppose we draw a card at random from a pack of 52 playing cards, a normal pack of cards, and we'll consider two events. So that's our experiment. The sample space then is simply the set of all possible cards. We could draw any card and doing it at random. One event we'll consider is the event where we draw a heart. So the card we draw is a heart. We label that event as H. And another event we'll consider is the event where we draw a face card. Label that as F. And so I hope you're familiar with how playing cards work. If not, it may be difficult to understand this example. But in a standard pack of playing cards, there are 13 hearts. There are 13 cards in each suit. Hearts is one of the suits. And there are 12 face cards. There are 3 face cards in each suit. So the number of outcomes in the event H, draw a heart, is 13. The number of outcomes in the event F, draw a face card, is 12. And now, if you think very basically, we're going to get into this a bit more detail in the next few videos, but the number of outcomes in a given event divided by the number of outcomes in the entire sample space is the probability that that event is going to occur if we assume that all the possible outcomes are equally likely. So counting the number of outcomes is related to determining the probability or chance that a given event will occur. And so, for example, since there are 52 cards in the deck, the chance of drawing a heart, if you draw randomly, is 13 divided by 52, or 1/4. We're going to describe this in more detail, calculating probabilities later, but the reason we're considering the number of outcomes in these events is because that's going to be related to calculating the probability of the events, assuming all the outcomes are equally likely. Okay, and so now let's look at a bit of an exercise. Let's find the number of outcomes in the event H and F, that's this one, and also the number of outcomes in the event H or F, this one. And we're going to show this particular relationship between these events, the event H or F, H, F, and H and F. All right. Okay, so let's look at calculating the numbers of these events. So first let's consider H and F. This is the event where you draw a card which is both a heart and a face card. So heart and face card. All right. And so the number of possible outcomes in this event is the number of cards which are both hearts and face cards. And there are 3 face cards in each suit, and so that means there are 3 outcomes in this event. All right, let's consider the other event, H or F. This is the event where we draw a heart or a face card. And we'll think about the number of cards which are either hearts or face cards. Okay, so there are 13 hearts. 3 of those hearts are also face cards. And then there are 9 other face cards, because there are 12 face cards total, but 3 of those are hearts. They're already been counted when we count the hearts. So the total number of cards that are hearts or face cards is 13, the number of hearts, plus 9, the number of face cards that aren't hearts. That's 22. All right, and so we figured this out. Now let's just check the identity, which is shown on the slide, which is what it asks us to check. And so we have that the number of hearts plus the number of face cards minus the number of hearts or face cards, or sorry, hearts and face cards equals the number of hearts, that was 13, plus the number of face cards, that's 12, minus the number of hearts and face cards, that's minus 3, and that equals 22. And that is the number of cards that are hearts or face cards. And so this is the identity that is shown there. Okay, so this is the end of the first video. In the next video, we're going to discuss the axioms of probability, which are the very basic properties we assume when we're calculating probabilities that certain events will occur.